Hi everyone, welcome to this video on pH and pKa. We're going to go over how to investigate the relationship between the two using the Henderson-Hasselbalch equation, and then we're going to look at how to find the predominant protonation state of molecules using these two values. If you'd like a free downloadable PDF of these slides, please look in the description below for the link. There is also a pKa table included within the slides for your convenience. Let's get started. So this equation is super useful for pH and pKa relationships. It basically says that pH is going to be equal to a functional group's pKa plus the log of the concentration of acid over concentration of base. Let's go through each part. pH is a value that tells you how acidic or basic a solution is. So a pH of 1 is super acidic. pH of 7 is neutral, so think of water. And then pH of 14 is all the way on the extreme basic side. So you can think of this as a spectrum from super acidic to super basic. This aligns with pKa because pKa values are also going from low to high, where lower pKa means more acidic and higher pKa means more basic. So it's basically the same trend as we see here with the pH. Now this log business is basically saying that if you know your pH and you know the pKa of a certain functional group on the molecule you're looking at, you can tell if there will be more of the protonated functional group or the deprotonated functional group. Let me give you an example. Say we had some molecule with a carboxylic acid. In different pHs, these carboxylic acids, let's assume we have a bunch of them in a solution. So times, I don't know, like 1,000,000. So we have a lot of these carboxylic acids. Now, in a pH of, let's say, 1, the carboxylic acid is going to be mostly protonated. So it's going to have this H right here. But if these millions of carboxylic acids were in a basic solution, then there would be way more of the deprotonated version than the protonated one. And you can see how that makes sense using the equation. We know that carboxylic acid has a pKa of 5. Since 5 is greater than 1, we can tell that the solution at pH 1 is way more acidic than the carboxylic acids. So the acidic solution would give protons to carboxylic acid and keep it as a protonated carboxylic acid. In terms of the equation, we can plug in these numbers and see what we get. pH is 1, pKa is 5, and that leaves the log part to equal -4. When the result of a log is negative, that means there was a fraction given here into the log. As a quick review of logs, let's say we have x equals log base b of y. This expression can be rewritten as b to the x power equals y. So in our equation here, we are essentially saying that 10 to the something power equals the concentration of base over concentration of acid. aka the concentration of deprotonated carboxylic acid and concentration of protonated carboxylic acid. Since we get -4, we're saying that this exponent is -4, which means this number has to be very, very small. To get this number to be very small, the denominator has to be way bigger than the numerator. So that means there's way more protonated carboxylic acid than the deprotonated version. You can also say there's way more acid concentration than base concentration. And we can find the same result if we plug in pH equals 14. We will see that we get 14 equals 5 plus some number, and with basic algebra we can tell it has to be 9. So that means our log expression is saying that 10 to the 9 equals the concentration of base over concentration of acid. Since 10 to the 9 is a very big number, we have to say, okay, that means the numerator is much bigger than the denominator. So there's more concentration of the basic deprotonated version than the protonated version. All right, let's apply our knowledge on an example. Let's say we have this amino acid phenylalanine, and we want to look at the functional groups and whether they would be protonated or deprotonated at certain pH levels. Let's start by first identifying the functional groups. Right here, I see our good friend carboxylic acid, and then here I see an amine. Next, we want to note down the pKa values for these functional groups. Carboxylic acid has a pKa of 5, and amine is a special case where it appears twice on the pKa table. So we're going to note down it has a pKa of 10 as a base and an acidic pKa of 35. Now, this problem can feel a bit overwhelming just because there are so many numbers to keep track of. But let's just focus on one part at a time. So what I like to do is compare pKa is less than, equal to, or greater than the pH. And it's important to have the pKa on the left of the pH for this case. I'll show you why in a second. Let's start with carboxylic acid. First, I'm going to redraw our molecule and leave out the H's because we don't know how many H's there are yet. But for carboxylic acid, 5 is greater than 1. Now, we can go through all the computations that I showed earlier, or you can use this neat little trick. So if you look at the bracket symbol I just drew, and you kind of add this line to the left, it looks like a P. And P stands for protonate. So this carboxylic acid would be protonated. And this makes sense because earlier we saw that, oh yeah, if we have a pH of 1, that means the solution is super acidic, so it would give hydrogen protons to the carboxylic acid, which has a pK of 5, so it's less acidic than pH of 1. Now let's go over amine. So amine has two numbers to compare. There's 10, which is greater than 1, and 35, which is greater than 1. When you have two pKa values to consider, both of them need to match up for protonating, so you need to have two P's. If you had something like a greater than and a less than, then you would keep the functional group the same. So the NH2 part would stay the same like that. But if you had two less thans, that would be like two deprotonates, then you would deprotonate the nitrogen. So in our case, we want to protonate our nitrogen, and since we started with NH2, this becomes NH3, and then nitrogen gains a plus charge. And we're done. So see if you can try out the boxes for pH 9 and pH 12. What are the predominant protonation states of phenylalanine for those? I'll show you the answer in 3, 2, 1. All right, for pH 9, let's start by comparing carboxylic acid. 5 is less than 9. And if you draw a dotted line here, it looks like a D, which stands for deprotonate. So that means we're going to get a deprotonated carboxylic acid. For the amine, 10 is greater than 9, and 35 is also greater than 9. These both point to the amine getting protonated. So we say H3 and give nitrogen a plus charge. Now for a pH of 12, let's do the same things. For carboxylic acid, 5 is less than 12, so carboxylic acid gets deprotonated. For amine, 10 is less than 12, and 35 is more than 12. Since we have this mismatch between, is it deprotonated, is it protonated, we can kind of think of these two conditions canceling out each other, and the amine would just stay a neutral amine. And we're done. I have one more practice problem for you to try right here. I encourage you to pause the video and try this on your own before resuming the video, where I'm going to go over the answer. So go ahead and give it a try. I'll go over the answers in 3, 2, 1. Remember that our first step is to identify all of the functional groups. So we got carboxylic acid here, amine, got an amide, and an ester. Now let's note down their pKa values. As we saw earlier, carboxylic acid has a pK of 5, amine has pK of 10 or 35, amide has a pKa of -2 as a base and 15 as an acid, and then ester has a pKa of -6 as a base and 25 as an acid. All right, so we got lots of numbers to compare. 5 is less than 12, so this carboxylic acid is deprotonated. 10 is less than 12, but 35 is more than 12, so this amine stays its neutral self. -2 is less than 12, but 15 is greater than 12, so this amide stays its neutral self. And then this ester, we would say -6 is less than 12, but 25 is more than 12, so it stays its neutral self. For pH of 7, 5 is less than 7, so we would deprotonate the carboxylic acid. 10 and 35 are both greater than 7, so we would take those two P's and protonate our amine, giving the nitrogen a plus charge. For the amide, -2 is less than 7, and 15 is greater than 7, so we would just leave it as is in its neutral state. And then for the ester, -6 is less than 7, and 25 is greater than 7, so we also leave that ester in its neutral state. For pH of 1, 5 is greater than 1, so we have a protonated carboxylic acid. For amine, 10 and 35 are both greater than 1, so we protonate the amine and give nitrogen plus charge. For amide, -2 is less than 1, while 15 is greater than 1, so we leave that amide as its neutral state. And then for ester, -6 is less than 1, and 25 is greater than 1, so we also leave that ester in its neutral state. And there we have it. Please let me know if you have any questions or suggestions in the comments, and hopefully this video helped you out. Thanks for watching.